Hello and good day. This is Dr. Fredericks again, bringing to you another video, this time on linear regression. Now, previously we went over correlations and we learned that Pearson's correlation is used to measure the degree to which a set of data points form a straight line or the degree to which a linear relationship exists between two variables. Well, that straight line that we previously called the best fit line is also known as the regression line. Regression is a statistical procedure that determines the equation for the straight line that best fits a specific set of data. Any straight line can be represented by the equation y equals bx plus a. You may have seen this equation for a line previously in math classes as y equals mx plus b. The concept is the same, however the letters or the symbols used to represent the values are different. The value of b is called the slope, and it determines the direction and degree to which the line is tilted. In terms of interpreting the value of the slope tells us what happens to y as x increases by 1 unit. And in the next slide, we'll look at this more closely. The value of a is called the y-intercept and determines the point where the line crosses the y-axis. Another way to describe the y-intercept is the value of y when x is 0. Now let's take a look at this scatter plot. Here we are looking at the relationship between total cost and number of months of gym membership. The relationship is described by a linear equation, y equals 15x plus 35, where y is the total cost and x is the number of months. Important to note is this is a perfect relationship with points directly on the regression line. If we look closely to the equation, we recognize that 15 is our slope and 35 is our y-intercept. Thus, as membership increases by 1 month, the cost of membership also increases by $15. If our slope was negative, we would say it decreases rather by $15, right? So our y-intercept 35 tells us that when you have been to the gym for 0 months, it costs $35. In actuality, $35 is the membership fee for the gym, which allows you to better interpret the y-intercept in this example. To determine how well a line fits the data points, we can define mathematically the distance between the line and each data point. Using the formula y equals bx plus a, it is possible to find the predicted value of y hat for any x. So y denotes the actual value, whereas y hat, or y prime as some texts write it, denotes a predicted value. And so the error or distance between the predicted value and the actual value can be found by y minus y hat. Because some distances may be negative, each distance should be squared so that all measures are positive. Otherwise, if you add the total distance between each predicted and actual value without squaring, you will always get 0. And so the total error between the data points and the line is obtained by squaring each distance and then summing the squared values. The regression equation is designed to produce the minimum sum of squared errors. Thus, the best fitting line has the smallest total squared error, hence why the line is called the least squared error solution and is expressed as y hat or y prime equals bx plus a. And this image depicts a more clear picture of the distance between the actual data point, y, and the predicted point on the line, y prime or y hat. And so the equation for the regression line is y hat equals bx plus a, where b is equal to the sum of products divided by the sum of squares of x, or an alternative equation for b is r, the correlation coefficient. You multiply that by the ratio of the standard deviation of y divided by the standard deviation of x. And a is equal to y bar, or the mean of y, minus b times the mean of x. Important to note is that y is referred to as your predicted variable or your criterion variable, and x is referred to as your predictor variable. A regression equation allows you to make predictions, but what it doesn't do is provide any information about the accuracy of the predictions. And so the coefficient of determination is r squared, and r squared is the proportion of variability in y accounted for by the variability in x. Kind of similar to the effect size eta squared that we looked at when we talked about ANOVAs. And the coefficient of non-determination is y minus r squared. And this is the proportion of variability in y not accounted for by the variability in x. And so, for example, if the relationship between two variables was 0.80, then r squared would be 0.64, and 1 minus r squared would be equal to 0.36, meaning that 64% of the variability for the y-scores is predicted or accounted for by the relationship with x. And the remaining 36%, that is the unpredicted variability. Occasionally, researchers standardize the scores by transforming the x and y values into z-scores before finding the regression equation. And so the resultant equation is often called the standardized form of the regression equation and is greatly simplified compared to the raw score version. And so the equation is y hat of the z-score, or the z-score, or the predicted z-score of y rather, is equal to beta times the z-score of x. First, notice that we're now using the z-score for each x value to predict the z-score for the corresponding y value. Also note that the slope constant that was identified as b in the raw score formula is now identified as beta. Because both sets of z-scores have a mean of 0, the constant a disappears from the regression equation. And so if you remember, or if you recall rather, the mean for a sample of z-scores is always 0, and the standard deviation is always 1. And so finally, when one variable x is being used to predict a second variable y, the value of beta is equal to the Pearson correlation for x and y. And this is only for the standardized form of the regression equation. Thus, the standardized form of the regression equation can also be written as the z-score of y, or the predicted z of y, is equal to the correlation coefficient of x and y times the z-score of x. And now r, which is beta for the standardized equation, is telling you what happens to y as x increases by 1 standard deviation. Thank you all, and I will see you soon. Take care.